Hello. Sorry for the state of the desk. I've had to clear it a bit for this. But I've tried to set up the experiment as close as possible to how we would set it up in school. We've got a retort stand, which we've clamped to the desk to stop it wobbling around. The pendulum is arranged in something called a split cork arrangement. There I've got a slit through the cork. We can put a thread through the cork, and it means that we can adjust the pendulum by pulling the thread up and down through the cork and just getting any spare bit of thread out of the way. And there's enough friction to hold it in place, especially when this is clamped tight. Whenever we're timing an oscillation from a pendulum, one tip that I often give is line it up so that the thread of the pendulum is directly in line with the retort stand. Whenever a pendulum oscillates backwards and forwards, we want to count the number of oscillations. And as you know, an oscillation is from one point in the oscillation through the complete range of motion and back again. So either from there to there and back, or from the center out, back, and back to the center. I recommend timing from the center because over time, the amplitude of the vibration gets less and less, but the center point always stays the same. So it's hard to judge exactly when a pendulum has reached its outermost displacement, but we always know when it's in the center. And I've lined up the camera here so that every time it passes through the center, we can count an oscillation. So if I would start 1, 2, and so on. Whenever we measure anything in physics, we have to make sure that we measure it to the correct level of precision. We're going to measure the length of the pendulum using a meter rule. As you know, a meter rule can measure to the nearest millimeter. Therefore, you must give your readings all to the nearest millimeter. If something's exactly 50 centimeters, you can't just write 50, you must write down 50.0. Or if you're asked to do it in meters, 0.500. I'm going to run through this experiment now. I'm going to take measurements for 8 different lengths of pendulum. I would recommend, if you have the choice, to do at least 7. 5 is an absolute bare minimum, but really at A level it's not enough. You need to do really as many as is reasonably practical. In a practical exam, you don't really have to do 2 or 3, but that will be defined at the time. But if you've got time in the lesson, you should be doing a good number. The more points that you have to plot in the graph, the more reliable your results are going to be in the end. So I'm just going to go through this and I'll speed it up. I'll share my results table with you at the end and my graph, and we'll compare it to yours and see what results we get. Always measure from the center of mass of the pendulum to the bottom of the cork. All 3 results are to within 5/100ths of a second. You want to make sure that your results are all nice and close together. Let's change the length, try again. Notice how the last time I just left the pendulum running the entire time. If the pendulum will keep on going for more than 10 complete oscillations, for 20 or for 30, you can just let it keep on going. Some pendulums will run out a lot more quickly and you'll have to start them again. This time seems a bit different from the other 2. The last 2 were 13.51 and 13.53. This is 1500th of a second out nearly. I'm going to repeat that one and see if we can get a better result. And our last one. Okay, that's all our results taken. A few things to note. Notice I didn't start timing when I released. I let it oscillate once or twice beforehand. That stops any timing differences between when you let go and when you start timing. The shorter pendulum sometimes started to rotate more conically or side to side, so we need to make sure that we keep it going in one direction. And a very important thing is, when you start timing, don't count one, go start 1, 2, and so on. I've seen plenty of people's count up to 9 really by accident instead of counting to 10. Okay, so now we'll work out our averages. Just make sure that we press equals before dividing by 3. Note here, my time was exactly 15 seconds, but I recorded it 15.00 because my timer recorded to 2 decimal places. Every single time was recorded to 2 decimal places because the timer does. Every single length was measured to 3 decimal places because that's 1 millimeter. You must record to the same precision as the measuring device. A few things I want to draw your attention to. Notice how I've written the units. I've got length / meters, time for 10 oscillations / seconds, time period / seconds. Maybe in the past and textbooks you sometimes see the units written in brackets or parentheses. You must not do that. They must be after a slash now. You will lose a mark in a practical exam if you put things in brackets. I've also made sure I've had a unit associated with every single column. You mustn't have any columns without units. So these are all in meters. These are all in seconds. And finally, our time periods in seconds. This was the time for 10 oscillations. So to find our time period, we have to divide this time by 10. Now, you might be tempted to write down, in this case, 1.621. That's not acceptable. What they will be looking for at A level now is that because our times are measured to 2 decimal places, in other words, to 100th of a second, we can't give our final calculated time to any greater precision than that. So we must also give this time to 2 decimal places, to the nearest 100th of a second. So in this case, this is going to be 1.62. This would go to 1.549, which is 1.55. 1.506, 1.51. 1.349, 1.35, 1.25, 1.15, 1.04, 0.93. So do watch out for that. It's not that they want the same number of significant figures each time, because these all have 3 significant figures, whereas our last value only has 2 significant figures. What they're looking for is that because our stopwatch measured to 100th of a second, our final times should be given to 100th of a second. Now we need to draw a graph. I had asked you to draw a graph with your dependent variable on the y-axis and your independent variable on the x-axis. Well, in this case, our dependent variable is our time period, and our independent variable that we changed is our length. So we need time period against length, and I'll draw that now. The rules for drawing graphs are very similar to what were expected of you at GCSE. Some things to bear in mind. If we look here, our smallest time period is 0.93 and our largest time period is 1.62. We need to make sure our scale covers that range. However, whenever we plot our points, they need to take up more than half the available graph space. So if I started down there and went 0, 1, 2, 3, 4, or 0.1, 0.2, and so on, I'd find that most of my results are squashed into the top part of the page with a lot of blank at the bottom. That's not acceptable. So what I'm going to do is I'm going to turn this page this way. My time period up the side, you need to make sure is labeled in exactly the same way as your the heading in your table. So time/seconds or time period/seconds. I'm going to go 0.8, 0.9, 1.0, that's 1.1, 1.2, 1.7. So height-wise on our page, our results are going to range from about there up to there. So they'll take up plenty more than half the available space. So one thing I forgot to say is that if your graph doesn't start at the origin, so in our case it went 0.8, 0.9, don't ever go 0 and then do a zigzag up there, because that becomes a non-linear scale. I know that might be allowed in maths, but that's not accepted in physics. Just go 0.8, 0.9. Our length along the bottom. Our results are between 0.2 and 0.65. So we could start at 0 there. And that means the results will go from about there to there. So they'll take up more than half the available axis. So I'm just going to plot the points now. So now I've plotted my points, and we have to put in our best fit line. Now, is that a straight line? Potentially, it looks like it could be a straight line, but it's not very straight. In fact, what would fit out much better is some sort of curve. In fact, if we kept on taking points down into shorter lengths, we would say that that is indeed the case. So what we need to draw is a best fit curve. Make sure that whenever you draw a curve that you orient the page so it naturally fits the movement of your hand. You wouldn't want to have to move like that. So you can always turn a page to make it fit like that. Work lightly and then put your line in a bit more heavily at the end. We want a single smooth curve. We don't want it a bit lumpy. It's a bit lumpy here. So we'll try and draw it a bit more smoothly. Don't forget it's a best fit curve. So if you have a line, a point that's a little bit above or below the line, that's fine. So up here, this isn't great. We've got what's called a train track. We've got two parallel lines. We need to erase that and make sure that it's a single smooth line. That's particularly important on any papers that you do that are scanned, because the contrast in the scan is such that it's impossible for a marker to tell the difference between a very faint line and a heavy line. They all just show up as black. And so it's very difficult to see what has been erased and what's been left behind. So here we've got a curved line. We don't know if it goes through the origin because we don't have an origin in our graph. But because it's curved, we know that these two things are not directly proportional. And so for next week, I'm going to look at how we can analyze these results, adjust them, and plot a new graph that is going to allow us to get something directly proportional.